Good evening.
Good.
Oh. Hi, everybody. Topcoder data science community. Good morning, good afternoon, good evening. Welcome to this pre-competition info session with the experts of the SpaceNet Challenge. The SpaceNet Challenge is looking to develop automated methods for extracting building footprints from high-resolution satellite imagery. This is actually our next installment in a series of image processing and computer vision challenges running on Topcoder. So be sure to stay tuned over the next few months for more, including a lung cancer contouring contest launching for Harvard Medical School next month. I'm Jen. I run our data science practice. I'm a main point of contact for many of you, and you probably hear from me all the time. And also from our stellar Topcoder team, I've got a few great people I want to call out. I've got our very own Nick Castillo, Clinton Bonner, and Andy Lamora. Thanks, guys, all for joining. So now on to the real good stuff here, the experts at the SpaceNet Challenge. I am going to introduce our guests. Just give me 1 second. Couple key points about this competition. One, it launches next week, so be on the lookout for that specific date, but it will be launching next week. And two, don't forget to go to our mini site. We've got a ton of content there for you, including this last week we added a visualizer for you to start playing around with, links to the data, as well as the scoring metrics to start reviewing. So lots of content. Utilize those assets because they're there to help you. Our format today is going to be 3 15-minute segments. We'll be ranging from background on the actual challenge itself. We'll talk through some formulation and humanitarian efforts, and then we'll also speak to the data. And when we're done with those 3 segments, we'll get to a Q&A session. So we'll do our best to answer all of your questions, but if you have any that we don't get to, we'll look to try to post those in the forum for you after this session is done. So without further ado, I want to introduce our guests. First speaking will be Todd Bacastow from Digital Globe. Second will be Todd Stavish from Cosmic Works. And third will be David Lindenbaum from Cosmic Works. And with that, Todd B., I'll pass it over to you.
Thanks, Jen. I'll go ahead and share my screen.
Great, and actually, Nick, we're not seeing Todd's screen just yet. We're seeing Dave, actually. Dave, can you go on mute for me?
It's actually working on the feed, so we're good.
1 second.
No problem. All right, it's all you, Todd.
Thanks, Jen. As Jen mentioned, I'm Todd Bacastow from Digital Globe, and before we get into some of the details of the challenge, I wanted to provide a little bit of context around some of our motivation and why we think this is an interesting problem. So with that, I'll go ahead and start my presentation. So we're really looking to harness machine learning to automate mapping, and we think this challenge presents a first step in helping to advance that. So before I dive in, I wanted to touch on 3 points during the course of this presentation. The first is, how are maps created? Why should we automate mapping? And what's the potential impact of doing that? So before we get into answering those questions, I thought, just as a level set, that I'd share just the definition of map. So I quoted the Wikipedia. So map is a symbolic depiction highlighting relationships between elements of some space, such as objects, regions, and themes. So as I think about that, I kind of wanted to distill what that means to me. And for me, maps provide a representation of place, which allows for common understanding. And I'm going to provide a few examples today of why we think that's so important and how we enable that at Digital Globe. So in terms of how maps created, well, so the history of mapping and cartography really goes back to drawing things by hand. Right, and so as you can see here, this was fairly low tech to begin with, and to replicate maps, in fact, you even had to trace maps that were already existing. So now moving into the digital age, we're much more high tech today, and there's mapping platforms such as OpenStreetMap. And I'm going to talk a little bit about how while it is much higher tech, the maps are online, in some ways, things really haven't changed. So this is a screenshot of OpenStreetMap. For those of you that aren't familiar with it, OpenStreetMap is kind of a Wikipedia of maps. So anyone can sign up for an account, go in, and edit the map. So the area that I've zoomed into here is Rio de Janeiro, Brazil. Let's go ahead and zoom in a little bit further to see what details on the map. So I zoomed into Copacabana. This is a popular tourist area of Rio, so well-traveled and populated. As you can see, as I zoom in, there's a lot more features on the map, so it's pretty well populated. Let's zoom in even further. So as I zoom into the street level, what you'll notice is that we of course see more detail. So we see points of interest, there's hotels, restaurants, shops, but what you'll notice is that there's actually, so in some of the city blocks, you see building footprints delineated. Other city blocks, you don't see building footprints delineated. And so are there buildings there? Well, of course there are. And when we look at satellite imagery, we can actually see that. So as I said, with OpenStreetMap, anyone can perform editing. You have to have an account, you log in, and you click the edit button that's in the upper left corner of the screen. When you do that, the base map disappears, and you actually see an interface that shows, well, you see some map features. We call these vectors, so points, lines, and polygons. You can actually see the satellite imagery in the background. And this provides an interface for creating map data. So going back to kind of the pen and paper example of tracing maps, this is a digital interface that allows you to actually go in and create map vectors. And in fact, you see with the red polygons that in fact some buildings have been created. But what's surprising to me is that for an area that's pretty populated and a popular location within Rio de Janeiro, there's actually so few building footprints versus all the buildings that you see, let alone if you go out to further out from the center of the city. So this is a good example how even in some urban developed areas, there's still the need to create foundational map data, and specifically building footprints. Typically the first two features that are created on a map, whether it's OpenStreetMap or other maps, are roads and building footprints to help define the baseline infrastructure. From there, then that allows people to focus on adding additional data such as points of interest, which you see on this map. But if the buildings aren't there, it doesn't make as much sense to add those points of interest. So let's change gears a little bit to another example. So beyond just sort of urban growth, I wanted to touch on how this can impact disaster response. The image that you see here was collected from a NASA satellite, and this is just, it's a beautiful image, but what's kind of happening on the ground is quite terrifying. So this is an image from October 4th of 2016 of Hurricane Matthew over Haiti. And when you look at the impact of that, so this is a digital globe image. I'm going to talk a little bit about our satellites in a minute and how we get these sort of images, but this is a before and after of the impact of Hurricane Matthew. So the before image is important to, of course, understand what was there. And creating this foundational map data that I mentioned, including roads and building footprints, is really fundamental in trying to understand what that infrastructure is. And then the after shot, of course, allows you to see what the damage is. And when you go in and create these map features, then we can begin to quantify what the impact of this sort of storm is. So then both responders and decision makers can allocate resources and provide help. So this interface is what's called Humanitarian OpenStreetMap Team, or HOT. And this is in fact a task manager that allows volunteers to go in and create map features in areas that the Humanitarian OpenStreetMap team has identified where map vectors need to be created. So again, there's great ways, great tools in order to manually create this data. Our vision is that if some of this data can be automated, then one, we can more quickly produce the data. We can also assist the crowdsourced mapping efforts. And we can also identify areas that perhaps that need to be mapped that we were unaware of. So we're, these are great efforts, and we're looking to help advance this discipline by helping to automate the extraction of some of these map features. So let me talk a little bit about our satellites and why we also think automation is important. So we currently have 4 satellites on orbit. I'll talk about our 5th satellite in a minute. We have some exciting news to share with the community. So today we collect approximately 3 million square kilometers every day. So that's about 70 terabytes of data. And the reality of this is that it's not humanly possible to have humans look at every single image or pixel that's collected. So even though we can use tools like the editors in OpenStreetMap or the other kind of mapping campaign managers, our vision is that eventually someday this will become part of our processing step, where we can extract the foundational map data to get that in the hands of end users more quickly, and also look at change sets in that data as well. So just to give you a sense of what satellite imagery looks like, so Digital Globe is a leader in commercial high-resolution satellite imagery, and this slide actually depicts all of our satellites actually produce data that's sub 1 meter. And so if the imagery that we'll be using for the challenge, we'll talk a little bit in the next presentation, but just to give you a sense, it's 50 centimeter imagery. And so this is very high resolution imagery. As you see on the right, we also produce 30 centimeter imagery as well from our satellites, Worldview 3. We will be releasing 30 centimeter data in the future as well to add to our SpaceNet data corpus. So the exciting kind of current events that I wanted to share is that so tomorrow we're actually launching our next satellite, Worldview 4. And so for those of you that are interested to kind of learn more about our business and what we do and really be a part of that experience, I encourage you to navigate to the bit.ly address that's below. We can certainly send out that link. So United Launch Alliance is facilitating the launch. And the satellite will be launched from Vandenberg Air Force Base. The broadcast begins at approximately 10:05 a.m. Pacific Standard Time. So it's a really exciting event to see one of our rockets go up and to really be a part of that experience. And so, of course, we're looking forward to having the satellite launch and then being able to, at some point in the future, get more and more imagery from these satellites. So with that, thank you very much, and I'll go ahead and hand things over to Todd Stavish. We're really excited to have you a part of this challenge, and look forward to seeing what algorithms you produce to help us automate mapping. Thank you.
Great, thanks, Todd. Todd Stavish, let's see if we can pull up your slides.
Jenna, are you going to pull your copy up, or should I do mine?
I apologize. I thought you were. Sorry.
That's all right. I can pull up mine if you think it's.
Yeah. Why don't you try?
Okay.
Go ahead and do that. Yep. See if it works.
All right. Can you guys see the slides?
We sure can.
Right.
Great. Go for it.
Okay, hello everyone. My name is Todd Stavish. I'm CTO at CosmicWorks. So I'm going to go over from a high level our data set, sort of, from a whole, what it is, and then some of the metrics and key dates and times in the competition. So first and foremost, I think Todd Boxtow alluded to this. This is the initial data set we're going to release. We're going to release a few multiple data sets, and we're going to host competitions around them all. So as you go through the competition, you learn how GIS and satellite imagery works. You'll be able to apply it on a series of competitions. But this is the first one we're doing. The initial public data set is over Rio de Janeiro, Brazil. It's from Digital Globe's Worldview 2 satellite. It originally came from a 50 centimeter mosaic. So Todd showed you the examples of resolution, or it's often called GSD. This is 50 centimeter, and a mosaic just means it's a combination of different shots from the satellite. A 3-band, which is visible light, RGB, everyone's familiar with that in normal imagery. But it also has what's called, of all the bands, the sensor on the satellite can take more than just visible light. It's called 8-band MSI. So when you begin to write your algorithms, know that there's more than just visible bands in here. And what we have found in our research in our lab is that these other bands are actually very helpful in determining vector features in the images. So keep that in mind. It covers in total 1,900 square kilometers. And our labels are building footprints. There's in the released public data set that you can use for your training. There's 220,594, and that covers roughly 252 square kilometers. And it's called an AOI. That's kind of satellite lingo. It means area of interest. Okay, so just to allude to the upcoming ones, we're going to release more satellite imagery over different cities. And that can be, again, there'll be another competition associated to that. And what we found looking at Rio has very unique geography, has very unique building materials and architectural styles. And so as we release other cities and other parts of the world, you're going to see other kinds of structures. And we think that's going to be important to sort of a general algorithm that can help us automate mapping. Pieces will be 30 centimeter, so we're going to up the resolution. It's coming off WorldView 3, the WorldView 3 satellite. It won't be from a mosaic, so it'll be from what's called a strip. So it's like a pure shot, one single shot. And we think that'll kind of, coming from a strip and high resolution, we think will be even better for algorithms. Again, we're including all 8 bands, and we're going to up the building footprints to 300,000. And then in the future, we're going to release vectors that aren't buildings. We're still kind of figuring out what would be best, but it would be infrastructure development kind of things like bridges or highways. It could be identifying agriculture or healthy agriculture versus unhealthy agriculture. It might be utility locations like oil refineries or electrical sort of power plants. We're still kind of working out our next non-building sort of data release and competition, but we'll update you as soon as we kind of work that out. Looking at the actual competition, this is on the website, but I'll go over it quickly. So we launched the initial challenge. We haven't, there's the visualizer out there now to help you self-evaluate. Also in the SpaceNet challenge repo on GitHub, there's code, if you want to, Python code at least, that you can add to your own code if you want to self-evaluate outside the visualizer. Visualizer is really cool though. It gives you a way to kind of render your proposals over the actual satellite chip. So both work, it depends what your preference is. It's about 34,500 total cash prize. We're going to split it across a number of different ways, like places and sort of sub-challenges, reoccurring competition, and data set release that we're going to go over a multi-year period. Those are the relevant dates. Again, those are on the website. You can see those on your own. So I wanted to point people to some open source code that was already developed and released. Development Seed is a sort of open source oriented consulting company. They released a sort of transformation scripts that can port SpaceNet directly to SegNet, which is a University of Cambridge neural network. It's right on GitHub. If you think that's a good approach to developing your algorithms, you can leverage the work that they've already done. A gentleman, I don't know his real name, but his GitHub handle is Oro Tripathy. He ported the SpaceNet dataset to Cafe, deep learning framework, to their single shot multi-box detector. That's out of the University of California, the Cafe network, or a sort of framework. NVIDIA, our hardware partner in the challenge, they've developed or they ported it to their DetectNet, which is on their digits framework, which also has Cafe below it. That's a really great framework. It has a UI built in, really kind of helps you kind of develop without a lot of coding. So it might be good for a first swipe, or if you want to code yourself, you can use that too to do some more detailed work. Partner Digital Globe released what they call their Deep Core SDK. It's more of an ensemble of different things, but that's a great place to look to begin your coding efforts. Again, that's also open source. It's in the Digital Globe organization on GitHub. And then finally, our lab, Cosmic Works, Dr. Haggard, he's on here if you have questions about it. He wrote a blog post with code snippets using TensorFlow, which is Google's framework that's analyzing building footprints from the SpaceNet dataset as well. Places to start, but by all means, use what you think will work. And I'll just put the URLs up for these. If you're going to watch this after the fact, you can do a screenshot or come back to it. I'll just leave it here so everyone can see the URL, so you don't have to hunt around in Google and stuff. Just real quick, the DetectNet, Parker, the NVIDIA guy that developed it, he basically stored his cafe model in a gist. So that's what is posted there. And then real quick, I just want to talk about our metric, like how we'll evaluate your proposed building footprints. We want to make it as fair as possible, and we didn't want to make it a pure sort of accuracy thing. So there's three main components. One is the polygon comparison. So we have a polygon that represents the building footprint, and you're going to propose one. And the way we compare those, your proposal to the label, the truth data set, is using intersection over union, or it's sometimes abbreviated IOU. It's basically an area comparison between your proposal and the real one. It's from 0 to 1, so the closer you are to 1, the more accurate you are in your guess. A metric have a threshold, which is basically, if you submit guesses, we'll take your highest scoring IOU, and it has to be above this defined threshold, which is 0.5, which is actually kind of a high threshold. And that gives you a true positive. That gives you a positive detection. So you have to have your highest IOU above the threshold that we've defined. We score. We have a single score at the end for all your guesses across all the image chips from the satellite image, and it's in an F1, which is standard. You can Google it or find it in Wikipedia. But the way we calculate the F1 is we do it by summing up all your guesses across all the chips and then calculating the F1. We're not averaging your F1s across all your proposals for all your chips. So we just think that's the fairest way to do it. And so we just want to be really clear. Again, this source code is in the SpaceNet Challenge GitHub repo. It's implemented in the visualizer. There's a lot of ways that you can kind of delve in and look into it. Okay, should have turned that off. Some Slack messages. All right, so I wanted to point out, like all truth data sets, there's issues. We've done our best to clean up what we could, but I think if you consider what's happening, and going back to Todd's, we have a satellite that's in space, outer space, hundreds of kilometers away. It's traveling at thousands of miles. It's taking a picture that's like on a sphere, so it's curved. And it's 3D, but we're representing it as 2D. Variety of ways that we create the labels, from leveraging some open source and crowdsourcing activities. And because, as I mentioned, this first data set's a mosaic, we have a time dimension. This is one of the issues that we've seen. We don't think it's widespread, but they're not uncommon. So this is one example. The building was demolished after the label was created. Sort of a misrepresentation here. So just be prepared for some inconsistency. This is one example. Here's another one. Again, as I was mentioning, we're taking pictures of three-dimensional structures, and so some tall structures, the building, because the way the satellite's pointing sometimes, or because of this concept called orthorectification, the footprint is not in a line with the top of the building. So that kind of thing can also happen. So be prepared to see that. Straight, a human made a mistake, or some inconsistency came into the image that kind of slipped through the quality assurance. You also see, back to this one, just a slight shift sometimes from the building footprint to the actual footprint. Example of this, but I've seen it in the data set. You'll see buildings of different materials, or perhaps different slopes or overhangs, and so you'll see the footprint deviate from the building sort of roof line. That's something to keep in mind. But I just wanted to give you a heads up. And again, on the next release, we're going to bump the resolution and avoid the mosaic and try to tighten up this. But in the first competition, this is an unavoidable part of the truth and the training data set. Pass the presentation on to Dave Lindenbaum. He's going to just talk about the actual formats, maybe some of the code, and just the structure of how to do your hands-on activities.
Thanks, Todd. Get our presentation. So just walking through, so all the data is up on AWS currently. The easiest way to find out where all the data is on is a list. It's the manifest.txt file that will be continuously updated as we put more and more information up on the SpaceNet data set. Right now, as we talked about, the first data set up is the AOI 1 RIO. So that's kind of the naming convention we're going to continue to go through with all of SpaceNet. As a new AOI comes in, it'll be AOI 2, AOI 3, AOI 4, and then we'll have the city name or the location name after it as some description. So the first thing we put up there is the raw data, which is actually the mosaic clipped into, in the case of the 3-band imagery, 19 or a little bit over 19,000 pixels by 19,000 pixel clips. Each one of those is about 100 megabytes, and that's at a resolution of 0.5 meter pixels. So it's not really easily consumable. The 8-band mosaic is at the same size, but it's actually 400 megabytes each, and it's 5,000 pixels a side. The other thing we have is the source data actually of the outlines. So the actual outline of that whole raster area we released where we actually labeled buildings, and the full building GeoJSON data set there. So that's basically all the source data for how we created the training data set. And they're all, so just a little bit about the formats. The GeoTIFFs, they actually have geo information that you can use various open source tools that we'll get into later to actually understand more details about what actually each TIFF file has besides just the band information. Next, actually, the contest data. So we went ahead and processed all that data. And what we did is did a chipping of the labeled area, and we created small areas that are each chip is 200 meters aside, and they're lined up so that there's a 3-band image, an 8-band image, and a GeoJSON that's associated with it, with all the building labels in it. So there you have a nice tarball that is a 3-band .tar.gz, that's about 2.4 megabytes. And then the 8-band .tar.gc is 848 megabytes. And then the actual labeled data set that comes with it is another 1.2 gigabytes. What we have is 2 different ways of providing the labeling. So we have a summary file in GeoJSON format, and then we also have a CSV. And as the test data will come out, you'll see how the CSV is actually labeled. It's pretty simple. There's an image ID associated with each building clip, or each image, and then for each building, there's a building ID, and then we actually have in pixel coordinates and geo coordinates the actual location of each image. It's kind of important to understand that all these images are on a place on the ground, so actually figuring out how to translate from the pixel format to actually the GIS format is a little bit tricky, but we built some tools to help you out, and there's a lot of open source to do that. So if you want to get started with the imagery and you have AWS, an AWS account with a credit card, you can actually sign up and just use the link down here to download the 3-band .tar.gz and start looking at what the data looks like.
Hey, Dave, I might just interject there and add too that the process to download this data is a little different than we're used to giving our competitors. That being said, we're trying to make it as painless as possible. So there will be a how-to guide and a what to expect in that how-to guide in order to access this data. So when we say you're going to put in a credit card, don't be alarmed. Don't think you're going to get charged a lot of money. We're talking, about 1 cent approximately per gigabyte of data. So we'll be providing you as much content on that as we can to make it as easy as possible.
Yeah, maybe just a little background. The reason why we have it in AWS is there's just export laws on satellite imagery, and that's just what we have to do to comply to it. It's not to make any money or charge you a lot. It's just required for the data set.
It's a good point to add. Yeah, and my one other point is that how-to guide will probably not be made available until the match goes live. That is likely to be the case. So just so you know, if you're looking to go download the data now, it's not there on the mini site yet.
Yep.
Sorry, Dave, back to you.
No worries. So that's kind of the format. We tried to make it up into every way. Also, the actual process we use to create those chipped images is actually up on our SpaceNet GitHub, and we'll be making improvements to that as we go along, as we learn more about different ways to make these functions easier for people to consume the data. So right now, it's a 200 meter by 200 meter image, but there's other ways to do that too. That was just the first one to pick. A couple of things to help you out. So besides the open source packages that were kind of released specifically for SpaceNet, if you want to get into the GIS side, there's a great open source GIS user interface called QGIS. There's also a open source package called GDAL. It has Python bindings and C bindings and C++ bindings. So you can kind of work along that if you actually want to start understanding how to work with geospatial databases. There are also a couple of Python libraries available. So there's Shapely, there's Fiona, and there's Raster.io. Shapely and Fiona, for the most part, work just with the vector data. So that's understanding polygons and buildings and how that all works. And then in the case of raster data, and which is the imagery itself, Raster.io works well with that. And then lastly, we have the SpaceNet challenge specific GitHub, which is up there, and we'll be continuously pushing new code out there as we find useful things. Feel free to jump on there and ask for different enhancements. And that's all I have.
Awesome. Great stuff, you guys. I love it. So next step would be to go over Q&A. So if Todd, Dave, and Patrick can just be on standby to unmute yourself if you think you want to comment, that'd be great. I'm going to start at the top, and I just want to add, anyone watching this live, you can drop into the chat of the live Hangout stream. You can drop your questions in, and we'll add them to the list, and we'll try to get them answered. So please do that. And I'll start off with, this is my favorite question. I think one of them, because I think it's fun for members to understand what you're going to be doing with the solution. So the question is, how are you planning to use the winning algorithms? Is this really just research only, excuse me, or will it make life better immediately? I'm going to guess the Todds. Sorry, not to call you the Todds.
Yeah, I'll jump in. Todd touched on this a little bit, but if you look at, Todd gave some of the humanitarian applications, but there's also just tech examples. Companies spend billions of dollars a year, Google, Nokia, auto manufacturing companies, to generate real-time maps. It'll help us do like autonomous driving, to make it safer. It'll help us understand where traffic might be at any particular moment. So there's a lot of transport sort of applications this can be applied to, in addition to the humanitarian ones that Todd highlighted. I'm sure other people have examples too.
Awesome. A follow-on to that, if you want to, actually, Todd, if you want to continue this one. So in general, how do first responders, USAID, humanitarian organizations, et cetera, use this kind of data specifically? I guess you kind of touched on it, but. Yeah,
well, there's one example that Todd didn't highlight, was during the earthquake in Nepal. They didn't understand the roads to access and provide aid to people. And so there was a crowdsourcing that just drew new supply routes around places that didn't have collapsed bridges or collapsed buildings in the roads. That's one example where real-time automated mapping would help people and potentially save lives.
That's really awesome. Yeah, we find that these more meaningful challenges, they really mean a lot to the competitors actually solving them. So that's great to hear that humanitarian angle. All right, next question.
Yeah,
maybe I'll throw. Oh yeah, please do.
Real quick. So yeah. I mean, to build on what Todd was saying, I think what we've seen with a number. I mean, even going back to the earthquake in Haiti, where OpenStreetMap really was noticed as a great source of map data. We found is that the map data that was able to be generated by tracing from satellite imagery was actually much more current than many traditional maps. So that aided first responders to understand if somebody said, well, here's where you need to go in order to provide assistance. If that place wasn't on the map, then they would have no idea how to get there. We saw that there's countless examples. There's the Ebola crisis in West Africa, where there were many places that weren't mapped. Many of the responders knew a name of a place, but they didn't know how to get there. So what we've seen, and of course Todd gave the example of the earthquake in Nepal. So we think this is, it's a great capability for both humanitarian response to help that. So the more that we can, not that while we're fully replace human mapping or analysis, but I think anything that we can do to help respond more quickly or help analysts get a time advantage so they can render assistance more rapidly. I think those are all welcome solutions. And then also as we increasingly get into looking at autonomous vehicles, as Todd said as well, there's all sorts of use cases for navigation and just keeping a current picture of our changing world. It can also be these algorithms can be used to also look at change, right? So how quickly is an area growing? Where is new infrastructure perhaps needed as an area continues to expand in urban areas? And another thing that I think we should also add too is that we intend to, for the winning algorithms, we intend to make those open source as well. So we see these as, certainly, that we're looking to help improve mapping for our own applications, but we think this will be of great benefit to the broader geospatial community, as well as all the many downstream applications as well.
That's great. I actually I have a kind of a two-part follow-on for you, Todd, and because the first is my just own curiosity, and the other, it leads into the next question. So how do you actually go about getting it into the hands of those responders? If we go in and really improve a solution, what's the means in which you get it into the hands of those responders? Because that's obviously critical, that that transition. And that leads me to the next question, which is explaining the partnership between Digital Globe, NVIDIA, Cosmic Works, and Qtel. So, and I'm guessing that's probably part of it. I think you're unmuted. Oh, no, you're not.
Yeah, sorry, just coming off mute. So there's a variety of ways to get this data into the hands of users. Let me just touch on a couple. So for users that are in a connected environment, we'll start with there. It's probably the easiest way. Platforms such as OpenStreetMap. What's really cool about that is as soon as you make an edit, there is a QA/QC process in the back end, but it more or less goes live, right? So this is something that it's fairly real time, and anybody who accessed that map could go in and look at that. They could review it. They could add information to it. So Digital Globe, we have our own mapping platforms as well, and platforms to provide satellite imagery. We have it's a platform called My Digital Globe. We also have a platform called GBDX, which is our geospatial big data platform, where we have our archive going back for all of our satellites. It's about at 90 petabytes of data. So the really cool thing about that is once these algorithms are developed, that would be, if you wanted to run that at scale to, for example, derive buildings over a large area, that would be an ideal place to run those algorithms, and then you could provide access to users there. Now, for other users that are in disconnected environments, there's a variety of ways to kind of package the data up, whether it's on disk or through other methods of file transfer, so they can take the data with them into the field, whether that's on a laptop computer or on a mobile device. And so we realize that for many disaster relief situations, either the connectivity may be lacking in general, or it may be damaged or destroyed due to the natural disaster. So we definitely want the data to be consumable in a variety of formats and a variety of form factors and modalities. I'm sorry, the second question was about
the second was
right?
about the partnership between everybody. If you could just walk through that for a moment, that'd be great. And then we'll switch over to data questions.
Great. Yeah, and I'll have the Cosmic Works team, also elaborate. So, in general, when we were looking at how to solve this problem, we were thinking about, well, what are the different elements that we need to bring to the table? And so, in general, for machine learning, what we continue to hear across the community in a variety of applications, and if you look at the success of ImageNet, I think it's a great proof point of this, is that you need labeled training data sets in order to enable or facilitate machine learning. And so that was part of the inspiration for SpaceNet, is that while there were a couple samples of data, there wasn't a large corpus of satellite imagery and geospatial labeled training data that was widely available. So that was really the inspiration for this initiative. We started that off with the Rio data set. As Todd alluded to, and Dave, we intend to continue to add to that corpus to grow it. And beyond this challenge, but we're really excited to work with Cosmic Works as well as NVIDIA, and so I think we each bring something kind of unique to the perspective of Digital Globe. We have our own and operated our constellation of Earth imaging satellites and have geospatial analysis expertise. Cosmic Works is doing phenomenal research around commercial space. I'll let Todd elaborate kind of on their specific interest, and I encourage you to check out their blog post as well, which highlight some of that research, as well as then NVIDIA is the leader right now with GPUs and really enabling machine learning and deep learning techniques. So through a variety, both on the hardware side, as well as through a variety of tools such as digits. Todd, do you want to talk more about kind of partnership from a CosmicWorks perspective?
Yeah, sure, no problem. So CosmicWorks, we launched around the rise of some of the Silicon Valley-based startups. There are a few out there that people may know of. One was a company originally called Skybox. Google bought them. They're building a constellation of smaller satellites around 1 meter GSD. It's a really cool company called Planet Labs. They're building CubeSats, which are basically this big. They could fit, like, you could hold them up. And they're taking like approximately 5 meter GSD, and they're going to have hundreds of them up there is their plan. So we saw all these sort of new sensors and constellations coming up, in addition to working with Digital Globe, who has, you know, the highest resolution commercially available. And we realized that, number one, there's going to be so many large data sets on satellite imagery, there has to be a new way. Historically, human analysts looked at them. And so we began to look at algorithm work to sort of automate that process, extract things from the images with software analytics. And again, we are publishing all of our research online, open sourcing as much of it as we possibly can. Our blog is called The Downlink. It's on Medium. It's DONLINQ. Take a look at it. Provide feedback and comments. But our goal is to basically research the newer commercial space world and publish it out as open source. We're a research lab.
Awesome. Great. Good answers, guys. Thank you. Appreciate it. All right, let's move on to some data questions. Here's one that's come in from a viewer watching live. And the question is, since there are inconsistencies in the labeling, including training data, what are you hoping to see from this algorithm that you don't already have today? For instance, apply current best techniques across more data.
We could let Dr. Haggerty answer that one if he wants to.
Sure, I'll tell you, man. I think the one thing that we wanted to learn from this competition is how to make best use of some of the extra bands that are available from satellite imagery that aren't available from sort of the ImageNet competitions. So the best use case now, or best state of the art, I don't think takes advantage of these extra bands, and I think that's really an interesting opportunity. Certainly, when you add the geospatial nature of it too. You know where you're looking in general. So is there information that you can include into your machine learning algorithms that take advantage of the geospatial information? Another aspect that I think differentiates this competition from sort of the ImageNet competition or similar competitions is that the scale of the imagery is extremely large. The objects of interest are relatively small in the scale. So just understanding the multi-scale approaches to machine learning and what works and what doesn't work, I think will give or will yield different architectures than are applicable in other scenarios. So I think just optimizing for satellite imagery, you learn about different architectures that work to identify objects in this corpus of imagery.
Okay, and I'll just take a pause and see if any of our other panelists would like to pile on to that. And thanks, Patrick, appreciate that.
Hey, Jen, while we're pausing, we actually have a real CubeSat in our lab. So this,
oh, cool.
This is how big satellites are now. This can take a picture from space. It's not much bigger than a camera that we used on the ground, maybe, I don't know, 50 years ago. They can now take them in space.
Oh, thanks so much for sharing. Has that one actually, is that just an in-office example, or is it really prepared to go into space?
No, that was I think from a production run that didn't have the quality to go into space. So it's a real model.
Awesome.
I'll do a quick Topcoder plug here. We've worked with NASA on some of their CubeSat programs. We're not directly installing software on it yet, but we've been able to have some visibility on this stuff. It's really cool. Even high schools are launching some of these.
It is really neat. Yeah, Andy, I'm glad you said something. We've both had a chance to work on those, which is really cool.
I do have one question, if you don't mind.
Please do.
Again, it's jumping ahead a little bit, but since we're in context, could you guys elaborate a little bit more on how the extra bands beyond RGB can be used to either improve the precision of the labeling that you have already, or just generally forward the goals here?
So I can, excuse me, I can jump in. So some of the extra bands include near IR, which can differentiate sort of vegetation and water from roads or building materials, and in some of the satellite imagery, that the colors aren't necessarily sufficient to demarcate the footprint of the buildings alone. It becomes difficult even as a hand labeler. If you start to use some of the extra bands, that distinction between the boundary of the road or the boundary of the building and the grass around it or the trees around it becomes much clearer. And just trying to find what is the optimal use of that those bands, I think, is a difficult question. And I think the promise is that for example, machine learning, for those of you who want to implement neural networks, that neural networks can learn how to best use these bands, probably better than even analysts that are trained to look at it can. So that's the hope. That's the promise.
Good question, Andy. Do you want to pile on any further, or that's it to an Andy?
No, but I reserve the right.
You do reserve. I'll let you have the right. You're fine. Go back on mute for now.
And there's something else I'll throw out.
Sure.
In the SpaceNet challenge repo, we're kind of a Python shop, but there are equivalent Java ones out there. A good project is OSGeo, has a Java GIS toolkit. So most of the stuff that we have in Python has a Java or a C++ equivalent. So I'll throw that out there.
Okay. Let's continue on this kind of this path of questions, a little bit more deep diving into the infrastructure of this competition. So are patented image feature descriptors such as SIFT and SURF allowed?
So SIFT and SURF are open source. They're part of OpenCV. I'm speaking. I think so. I'm not totally sure about their licenses, but I think we're not using it in a commercial application. So if it's relevant to a solution, I don't think it would be prohibitive, but I'm not a lawyer.
I'll pile on. So just assuming you say no problem with those two feature descriptors. For us, it's just a matter of making sure the client can execute and use it without having to pay anything. It has to be fully explained how you're using it, and we have to be able to replicate it. So no cost, easy to replicate, well described, and open source is, at that point, is pretty much, I think, key.
Mm-hmm.
Okay, so next question is, can competitors use external data or public pre-trained model or weighted data? And I kind of know the answer, but I'm gonna let you guys answer first, and I'll pile on.
I broke up when you asked the question. I didn't hear it.
Sure. Can competitors use external data or public pre-trained data? I'll leave it at that.
I think for the purpose of this competition, we'd prefer that you use the SpaceNet data set. I think that would be the most honest way to approach it.
Yeah, and I think I actually think in our contest statement, we have specifically stated that we want them to only use that data for this competition. That doesn't mean that in the future that may not evolve, but for right now, I think that's the approach on this match. And so the next question doesn't really matter because it's what external data, if any, can be used, but we sort of just explained that. Here is a question. What is the expectation on the achievable F score? Wow, I see grins.
As best as we possibly can get. Patrick, you've probably done the most work, like on your sort of prototyping. Maybe you can give a realistic range.
Yeah, on our blog, the downlink, not to pitch it too much, but I did a walkthrough on how to build a pretty simple network to identify footprints, and without any optimization and even long train. I think the training took at most a couple hours. I got an F1 score in the low 20%. That's not. I don't think that is great. I think that can be improved upon through this competition. Just to put other F1 scores in context, so a lot of object detection competitions, they work with bounding boxes. We're not working with bounding boxes. We're actually working with the polygon that describes the building footprint. And if you were to just submit the bounding box for their footprints using the ground truth, the F1 score you'd get would be, I think, 79%, which is, I mean, it gives you a little relevance. So if we were able to improve over that score, I believe that it would demonstrate that you're getting better than the bounding box approach. So that would be, I think that would be considered a success.
It's actually very helpful context. That's not something that I think we've actually written down or explicitly said yet. So that, Patrick, that's really helpful, and appreciate you sharing that. All right, next question. I like this one. In this competition specifically, and with this data, what is the definition of a building? Is there anything better than whatever is labeled as such? Related to this is, what were the exact labeling instructions given to the annotators? So if you could just sort of walk us through that, that'd be great.
That's probably done best by Todd Backestow. Is Kyle on the line? I don't think the label expert is here.
Yeah, Kyle's not on the line, but let me just speak to it a little bit. So with some of the examples that Todd Stavish showed. So the building footprints that were produced for Rio were, it was, as Todd Stavish mentioned, off of the 50 centimeter mosaic. And so essentially what we're trying to do is, in general, you want to, as close to on nadir imagery, which means kind of straight down in general. Now with the mosaic, the one challenge is that it's a combination of the images. So you're going to have some that are closer on nadir, some that are not. So in general, what we're trying to do is produce a two-dimensional polygon that would most closely represent, if you were to look straight down over the building, where essentially the base or footprint of that building would be. Now, oftentimes that may be, what you can see from space would be delineated by what you can see on the roof. So one could infer that in fact that would be representative of the footprint as well. So it's while we are calling it ground truth, I mean the only way to truly get ground truth with a building footprint would be to actually survey kind of the base of a building. But it would be nearly impossible to do that at scale across a large area like Rio. Another thing that we should mention as well is that we've tried to identify fairly regular polygons. So you'll notice that in the chart that Todd Stavish showed, the area of interest, or kind of the outline that we've selected for this particular challenge, it's kind of an odd shape. The reason for that is that we tried to select out certain areas where while there very well may be structures, the geometry of those structures is not as kind of cleanly defined, and so eventually it'd be very interesting to be able to extract that kind of data as well. We wanted to, given that this is kind of a hard nut challenge, though, we wanted to simplify that as much as possible and have a regular polygon type building structure. So Todd, do you have anything to add, or do you think that answers the question pretty well?
I think you did a great job, but I would personally volunteer to go to Rio and measure building footprints for 6 months if that's on the table. But yeah, I think you did a great job. It's a three-dimensional problem. We did our best to simulate the footprint.
Maybe if you win the prize, you could actually wait. Sorry, you're not eligible, so forget about that.
All right, just had to come off mute. So I actually got a question that's a follow-on to one I sort of already asked, but I didn't see it until just now. So let's go ahead and we're going to go back to it. So this is the question is this: on the NVIDIA blog, there are some scores, and here's the examples of what they've seen. The mean precision and recall values across the building bounding boxes in the validation set are 47% and 42% respectively. Is it for a training validation setup comparable to this contest? Is it for a training? I'm not sure if
I'll respond to that. I think I know the blog that you're talking about.
Okay.
And I believe those numbers took the bounding boxes of the ground truth labels and used a TechNet to create new bounding boxes. So I don't think it is the metric that we're using. It's similar and it's a little confusing. Certainly, even from what they were computing the IOU with respect to. we're not we're using the actual polygon from the label to compute the IOU, not the derived bounding box. So those numbers are probably I don't know how they compare to different algorithms, but that is out of the box to TechNet. So that's one thing. Another thing about the mean average precision, we use the F1 score instead of mean average precision because a number of the chips of our data set don't have any buildings in them. And so in order to properly define your recall and your precision and have that be a useful statistic, you generally know how many objects there are in each image. So the reason why we aggregate over all the imagery is that's more appropriate for a diverse set of sample imagery that has, some have a large number of buildings in them and some have zero. So that's why we aggregate as opposed to using mean average precision. So those numbers don't directly translate to our F1 score, but thank you for the question.
Awesome. Okay. The next question I'm actually going to go ahead and answer. And Andy, you're welcome to piggyback on it. So the question is, how much can we expect to pay to download this data? Anything, question mark. So there's a little bit here to this answer. So if you are new to Amazon and have yet to download any data, for this competition, it will actually be free. There is I think 15 gigabytes of free data that you can download when you're a new user. You do have to enter a credit card. That is unfortunately a step that must be done. But it's really just that, a step of entering a card that doesn't get charged. If you are an existing Amazon user and have already downloaded the set amount of free data you can download for the month, then you're looking at approximately 1 cent per gigabyte of data in addition that you need to download. So you're looking at maybe, a few cents up to maybe 15 cents. So a really small, in some people's minds, even almost free amount, but it is a step that our competitors are not used to having to do. So we're just trying to be really upfront and transparent on what expectations will be for this match.
Hey, Jen, the only thing I'd pile on is if anybody has any concerns about this at all, to post in the forums. I'm not sure if we have the challenge forum up yet, but put it in the general forums. We'll hit it.
Yeah.
I think we're very happy to talk through it with people. And and also, if you have a real concern about the cost, if you think it's going to be different, or you're concerned about your own ability to pay the cost, bring that up to any question at all questions.
Thank you for bringing this up. So the challenge forum is not live yet. It'll go live the minute we launch the match, but the general forums, absolutely. Please go hit those questions there. And between the co-pilots on this match and the top coders, we will address everything and again, make this as painless and easy as possible for everybody. And just know that there are more SpaceNet challenges in the queue. Both Todds have already suggested that there's more data coming into that data corpus, more challenges coming on Topcoder. This Amazon data download process will continue to be the same. So again, we'll look to make this as simple and easy as possible, but might as well start now getting used to it because these are cool challenges to be a part of.
Yeah, I'll just add, it's S3, which is what we're using to host it. It's the public, Amazon hosts public data sets for people to do research on like this. And our current data set is, Dave correct me, it's below 5 gigs. But the next ones that are coming, they're getting larger and larger. And even though, again, there's sort of this administrative thing you have to do, it is a really great way to share large data sets. So I'll throw that out there.
And I'll pile in with one more thing again. As Jen said at the top of the call, we have a how-to that'll walk people through it. So be sure to check that out.
Very good. So we have 1 minute left. Oh, go ahead, Todd. Please go ahead.
So, as Todd alluded to, so all of the Amazon public data sets are actually, they follow this request or pays model, and really, so Amazon's providing the hosting for this, and so really all it is it's the transfer, it's the cost to transfer the data, and I believe actually if you keep it within the same region of Amazon, there's also no cost to do that. So it's only if you're downloading the data, and as you said, it's a fairly low cost in order to do that. And part of the rationale, just to explain it as well, is that, as Todd said, we're expanding the amount of data, and we really want to keep that corpus kind of in one place as opposed to kind of replicating parts of the data in different places.
So we have like less than a minute, and I think we've touched on everything I wanted to, but there's one question I think we can answer with like a 1 or 2 word answer, and that is a follow-on to what were the exact labeling instructions that were given to the annotators. The question is was the data created by human annotators or algorithms?
So it was actually, this data set was actually a combination of a little bit of both. There were some semi-automated tools. Then it went through a QA QC process, and then we actually so because it's a mosaic, we also went through and did the best we could to ensure that it was aligned to the buildings. As that said, as the examples were showing, most of these data sets aren't perfect, so we wanted to be upfront to say that there are some anomalies. So we do think that the subsequent releases we've now switched to the additional data sets that will be used in future competitions are actually all hand labeled. We're finding better results and more consistency. And then, as Todd said, we're just using a single image as opposed to a mosaic. So this is a way to get started, and we think there will be continued improvement there. But hopefully that gives some context.
Great. I lied. I'm going to let one more question pop in. Sorry. But we got to do this one really quickly, please, if we can. So please give more details about the band frequencies. Specifically, we were asked if we could list all the frequencies. And feel free to answer what you can here. And if need be, too, we can add some of this content into the forums or into the contest statement, too.
So I on my blog, on the Domlink blog, I briefly link the frequencies associated to the Worldview 3. Todd B can probably give you more details, but those are publicly available for the sensors that are on the on that satellite. So I think, and just without looking at the blog, it's going to be in the visible spectrum range and some near IR. So those are the frequencies that I'm aware of, the labels. But from a research perspective, I know there's correlation between the data in each of the frequency bands. But when I trained my neural net, I didn't use that information. I let the neural net learn the correlations and try to optimize the use of each of the bands. So.
Okay.
Yeah, I think
Thanks,
Patrick
Patrick.
covered it. If there's any additional information that we can post, we'll provide that as well as a reference.
Great. So I just want to, final words, say thank you so much to this panel of experts. Patrick, Todd, Dave, thank you. We're so excited about this challenge that we get to host it on Topcoder. So look forward to debriefing when the challenge is done, and good luck to all the competitors competing. Again, launching next week, the exact date, coming very soon. Thanks to all the Topcoders who helped support this call. Andy, Clinton, Nick, thank you. And with that, we will sign out. Thanks, everybody. Take care.